Good morning, everyone. This is a Concepts for Future Detectors session. We have 8 talks here today, so the slight delay here should not be too much of an issue, as we initially had planned 2 times 10-minute break, which are maybe not so urgently needed for a Zoom session, so maybe we can still finish in time. However, I would very much like to ask the speakers to keep within the time slot. So there are 15-minute talk plus 5-minute break slots. So please try to keep within those slots. And then I would like to start with the first talk and give the floor to Antonio, who will talk about astigmatic mode mismatch sensing for the next gravitational wave detectors.
So thank you once again for having me here. I'm going to talk about astigmatic mode matching sensing, which is just an extension of the mode matching sensing. So the summary of my talk will be I'm going to talk about the theoretical model, but just to mention where it comes from. And I'm going to describe a bit of our experimental setup, and I will walk you through the first experimental results. And I'm going to describe the plan for the future. So why am I going to talk about astigmatism is because we all know that from the studies, the previous studies, in order to have the full functionality of the squeezing technology, we don't want to have losses. So losses are our enemies, but there are different type of losses. So one of the major, the more dangerous one is are losses due to the mode matching. The requirements are very strict. Losses due to mode matching cannot be more than 2%, at least from the previous study. But when we talk about mode matching, we always assume, well, most of the time, we assume that the mode matching is something that is related to losses of a circular beam inside a cavity. The key point here is that is not something that is related only to symmetric beam. We have losses and we cannot easily discriminate in general from the symmetric one. So something happened. I'm sorry. I need my slide to be here working. For some reason, it's not going into the direction. So I go anyway. I'm sorry, but it was an important slide. It went through. Okay. So I just want to say that when here there was a picture that we don't see it anymore. When we want to have a mode matching, a proper mode matching, we have to inject a beam into the cavity. And the cavity has somehow from the geometrical design imposes the type of the Gaussian beam that has to enter. So if the Gaussian beam is not perfectly matching what the cavity requires, the eigenfunction, then you have losses. But we always, as I was saying, talk about a symmetric Gaussian beam. When we talk about mode matching. In our work, we discriminate by losses due to mode matching for a symmetric beam and losses due to astigmatic beam. The theoretical model that you see here, I'm not going into the details of this, but it's a common Gaussian beam a Gaussian beam where we use the approach of Anderson that has made in the past, where we expand the modes, and we see that there is a contribute due to the second order modes. Unfortunately, from here I don't see my. So this is the common model for a symmetric mode. What we did is we gave a second dimension. We just considered not only the x or y axis being the same, we consider different x and y axes. So here we can see, we can recover a bit of what I was saying. So instead of injecting a beam that is not matching the cavity, but having a symmetric beam, we break the symmetry of the beam and we inject the beam that is not matching the cavity in two ways, in the x, for the x section and from the y section. For example, here we consider the x zeta plane and the y zeta plane of the beam, of the traveling beam. And the x zeta plane, for example, does not have the waist into the right location. The y zeta does not have the right sides. So in order to have a perfect matching of the cavity, we want to have the waist location and the waist side exactly in the position imposed by the geometry of the cavity. Here we are breaking, we are putting one section with the waist side somewhere else, farther away, and a different size. So we do it mathematically and we get basically somehow the same expression that we had for the symmetrical one, but appears in our model. What we found is the different modes, higher order modes, are appearing. For example, what you see from the expansion, considering the two sections, we have the emit Gaussian mode 1-1. So we have a common contribute, which is related to the mismatch of both the sections, and we have a differential contribute that is a combination. Sorry, it's the other way around. The symmetrical one, which is a combination of the 2-0 and 0-2 modes, and then we have also the differential part that is still a combination, but is a sign that changes. Plus a contribute that is given by the 1-1 higher order mode, so second order, but 1-1. So as you can see here, there are different shapes of the modes. This is what we are going to use. So just to resume what I said about the model. So when the cavity is mismatched, the cavity sends back LG10 mode. We apply to the reflection of the cavity a conversion with the mode converter telescope, and we transform the information coming from the cavity in a higher order modes, and that we can read and we can sense, giving and understanding the information related to the symmetrical mismatch. So the LG10 will be converted in HG11 with 45 degrees rotated. Then we have the other way around, but we do this operation just with the mode converter telescope. And the mode converter telescope convert the modes, and then will be modes that are before were in LG1, so in another basis, they will be converted in emit Gaussian mode, and they can be read from quadrant photodiodes. But if we add a quadrant photodiodes before the mode converter, we can basically sense the H11 rotated mode that gives us information about the astigmatism, which is in addition, it comes on the top of the mismatch due to the symmetrical beam. So there is no time to go into the details of the setup, but the principle was given. We did this setup with the cavity. We applied, we verified that the mode converter works. We obtained a linear signal for mode matching, for the mode matching, the symmetrical one. So basically, we placed the quadrant 1 and the quadrant 2 photodiodes, quadrant photodiodes, to detect, to sense the mode matching, the symmetrical one. Then we tried to, we did it for both the photodiodes in a different quadratures. And then we did the experiment putting the photodiodes, the quadrant photodiodes, before the mode converter telescope. And also imposing an asymmetric mismatch by putting a cylindrical lens on the top of the screen. I don't have, unfortunately, my prompt here. I cannot show you. Is in the orange side. So there is the cylindrical lens. We applied the astigmatism, and what we found is that after the mode converter, we still detect the mismatch in case it is. But if we just apply the astigmatism, we are not going to detect any mismatch due to the mode converter, to the symmetrical beam. So we completely discriminate from the symmetrical one to the asymmetric. So we imposed the astigmatism, and we found the results also for the beam in astigmatic condition. You see the quadrant photodiode, the yellow one is the one that is before the MCT box, which is the mode converter telescope. That one is able to detect the H11 high order modes. So we rotated the lens, we imposed the astigmatism, but we can see only losses on that photodiodes, and we could, I mean, we are approaching to validate the model and also the results. The results are really promising. We couldn't get a linear error signal because we had only one cylindrical lens implemented. We needed to have more cylindrical lenses to impose a linear variation of the astigmatism. But the model fits completely with the measurement, with one lens. So what we are going to do is indeed is to implement a second cylindrical lens to have an astigmatism induced in a way that more generic way, and we want to have more quadrant photodiodes because we didn't have enough quadrant photodiodes to be in order to detect both the symmetrical mismatch and the asymmetric mismatch. And also the measurements are affected by the misalignment of the cavity. We are going to implement also piezo a mechanism to keep the cavity aligned properly. So I think I lost the track of the time, so I think I can stop here because things are not working on my computer.
Thanks, Antonio. Does anyone have any questions for Antonio? So if anyone has any questions, please raise your hand so that we can do this in an ordered way. Yes, Sheon, please.
Hi there, can you hear me? Okay.
Yes.
Yes. Oh, okay. Thank you, Antonio, for your talk. Just two very quick questions, or maybe I might have missed it, but all right, I'll just ask anyway. The first one is, can you give us an idea of how sensitive your idea is to, like, for example, the cavity's waist size? So if you have like a really tightly focused cavity waist, i.e. a high growth phase change, does it help your setup?
It may be, but we are not, we didn't explore too much this. But what I can tell you about the sensitivity about the setup, we can detect, we can sense the mismatch at 1/10 of what we can measure with a beam profile in the cavity. So basically, if I measure the beam waist or the location with our beam profiler, there we are not so sensitive. But with the sensing system that we have, we can have information about 0.001%.
Okay, great, thank you.
You're welcome.
Thanks. Any other questions? Seems not. Then thanks again, Antonio.
Thanks to you.
And then please unshare so that, yeah, the screen is free for the next one, who is Zhang, who will talk about development and characterization of a picometer-sensitivity sensor for suspension platform interferometry. Please go ahead. Yes, we see your screen already.
Yeah, so yeah, good evening, everyone. My name is Zhang. I'm a postdoc at the Australian National University, working within the Center for Gravitational Astrophysics, or CGA. And in fact, this evening you'll hear from 4 of us within CGA. So my talk is going to be about a project that I've been working on since I started here, which is developing a suspension platform interferometer. So let's dive straight into it. So I want to start with the seismic challenges in the LIGO interferometer. So if we think about it, the detectors occupy a very large footprint, and there are these chambers which house the key optics for the LIGO detectors, and they're separated by these vast distances, meaning that environmentally they can experience very different seismic profiles. And it's really the differential movement between these chambers or optics that we need to worry about. And as such, one of the potential mitigation solutions is to develop some sort of sensing scheme to really track their movements and feedback that signal to stabilize these platforms. One of these schemes is called the suspension platform interferometer, where we can deploy 3 optical links and measure the changes in length over 3 degrees of freedom. So having them at different heights will allow us to obtain information about not just how they're moving parallel to each other, but also the differential tilt between these 2 platforms. Obviously, with LIGO measuring as such extreme sensitivities, we want to have good stabilization as well. So the best way to achieve that is to use optical interferometry, obtaining some of the highest sensitivities possible. There's been a few efforts looking into this across the globe at institutes such as the University of Tokyo, AEI, Stanford, and finally us, ANU. And we need to remember that when we think about the implementation, these platforms are going to be housed within these vacuum chambers. So the ease of operation there cannot be understated. And with that in mind, this is the design that we've come up with for our suspension platform interferometer. So we use a hybrid Mach-Zehnder-Michelson interferometer where we split the optical beam into a signal arm and a local oscillator. The signal arm is then split again to interrogate 3 free space optical links. Now, the way we separate these free space channels is by using digital interferometry, which deploys a pseudo-random code modulated onto the optical beam. So through optical propagation, all we need to do is to ensure that each of these channels have a different optical time of flight. Therefore, they'll have a different delay on the optical code upon interference. And following that, in digital signal processing, we can delay our digital code to try and match with the optical code. When that happens, we recover our signal of interest and reject any other signals outside of that range gate. So by constructing an experimental apparatus like this, in terms of implementation, all that's required is a few vacuum feed-through connectors, and the rest of the setup can be packaged into a relatively compact box, which we call the injection box. So that's to play at the strength of a optically simple setup. Now, one of the unique challenges that we've encountered with digital interferometry is the crosstalk suppression that we're able to get out of it. So the pseudo-random sequence has a autocorrelation profile, which ideally looks like this. So when you have your digital delay matching with your optical time of flight delay, you recover a huge peak. But at any other mismatch delays, the resultant amplitude should be very, very suppressed. But the use of pseudo-random sequencing is by nature a broadband, spread spectrum technique. So it really requires us to capture all of the spectral information to take full advantage of this. In the real world, obviously, our electronics have bandwidth limitations. So they could be AC coupled, meaning they don't capture all the DC components, or they could have a low-pass filter at some higher frequencies, meaning that they reject any higher harmonics. So this can really lead to a relatively compromised autocorrelation performance shown here on the right. So the green, again, is the right-hand side of that ideal correlation, and the red is what we actually get experimentally. So you can see that we don't immediately reduce down to almost 0 amplitude immediately after the initial signal. So that means that we need to work around it. And the solution that we're currently utilizing is to simply lengthen the delays between all of these demodulation channels. In practice, we've found that about 5 meters of distance tends to be good enough. So having talked a lot about the experimental configuration, how does it actually look like in the lab? So here we have some pictures. We have all the injection optics previously shown as the trolley box, installed here on this little breadboard. And then it splits into 3 channels, plugging into these partially reflective collimators. So they reflect about 50% of the light, and the rest shoots out to interrogate these and corner cubes. And so we demodulate individually the interference of what we call the prompt reflection with the local oscillator, and then the end reflection with the local oscillator. And we take that subtraction to obtain the displacement signal between these 2 guys. Now, so that was the first implementation of the experiment, but we quickly realized that having everything just simply sitting in the laboratory air wasn't sufficient. There's a lot of air convection and a lot of long-term temperature drift, which we really had to mitigate. So to that effect, we did 2 things. Firstly, we packaged up the injection box into this little thing. And for the real measurement part, which includes the free space optical link, we put that into a thicker box. So this box, nicknamed the coffin, is made of 20 mil perspex. And so this is kind of an initial attempt, and then we quickly realized that wasn't sufficient still. And it wasn't because the thicker box did do a pretty good job at blocking out air current. However, the way it was assembled meant that there was actually some thermally driven mechanical coupling between the base of that box into the optics. So in the second iteration, we installed some mechanical isolators underneath the optics to really decouple them mechanically from the perspex base. And we also realized that a thin box for the injection optics wasn't quite enough either. So we added these polystyrene panels to the faces of that smaller box. So now it looks more like an ASCII. So that's a lot of talking about the setup. What does our performance look like? So here we have the displacement spectral density of 2 of our sensors plotted here, and they actually track with each other fairly well. So you can't really tell them apart on this plot. And then we take the difference of their time domain readout and plot the FFT of that in green here. So the difference here really theoretically cancels out all the environmental displacement and gives us an estimate of our noise floor performance. So we can see that we achieve better than picometer per root hertz above a frequency of 0.5 hertz. And at our target frequency band of 0.1 hertz, we're sitting at roughly 3 picometer per root hertz, which is not too bad. We still have a fair bit of low frequency roll-up, and that's likely due to the residual convection as well as temperature effects that we didn't completely mitigate with the boxes. Now, you would have also noticed these 120 hertz and above harmonics. And this is actually because we use a sawtooth frequency modulation on our laser to mitigate cyclic error. So cyclic error is caused by the I and Q not being completely matched with each other. So the I and Q of our phase signal can be firstly offset from where they should be. And then they can also have a different gain on them, causing, if you think about the interferometer phase rotating like this, the resultant phase is not a perfect circle, but instead a ellipse. But our demodulation doesn't know that. So as far as demodulation is concerned, the interpreted phase is plotted here as the red, and you can see on the right plot here that they tend to deviate from each other, causing what we call a cyclic error. Now, with the sawtooth frequency modulation, what we're essentially doing is that we're driving the laser frequency to create a cyclic phase modulation at a deterministic frequency. So we're essentially collecting all of that cyclic error into a deterministic frequency bin. And in our case, in the previous plot, that all goes into the 120 hertz frequency bin. And our low frequency is, as a result, free of this cyclic error. Now, so we've extensively characterized and tested this SBI inside our control laboratory environment. The next step for us is to move it more towards an in-cavity test. So we're proposing this joint experiment with the University of Western Australia to install our SBI sensors in the 7-meter cavity at the Jingjin site. So what we're planning to do is, over here we have a rack which sits within one of these tanks, and we want to place 3 sensors at these locations, and they should all have direct line of sight with respect to the other tank. And on the other tank, obviously, we'll have the reflectors. So what we're really hoping to demonstrate with this is east locking requirement and hopefully a lower RMS error signal for the Jingjin cavities. Yeah, so that's it for my little spiel. Happy to take any questions.
Thank you very much. Any questions for Ya? Okay, if no one has any questions right now, you can, of course, also contact Ya later on, I assume, if anything comes up later. And then, yeah, thanks again. And then we just go ahead with the next talk. So next one is Mario, who will talk about stray light noise simulations.
Okay, hello everyone. So let me start the talk. I think you heard me well. You see the slides. So, oh, okay. So I'm going to talk about the stray light simulation. The talk has 2 parts. One is simulation themselves for ET. Where I'm going to talk about beam losses, apertures, give some consideration about baffle layout. I will give you some preliminary noise estimations inside the ET main tubes. And then I want to take some notes on the instrumental baffles for Virgo and how this is actually being now expanded to large mirrors. And at the end, I will make some final notes. So basically, let me go into the ET simulation. So the thing is that the first consideration for ET is how wide the tube should be and whether we are limited by apertures and beam losses. So essentially what we did was to, for both low frequency and high frequency configurations, we look into what was the level of clipping losses, and then how this would essentially condition the dimensions of the vacuum tube. So what we did was to simulate the beam profile you see there, and do this for a given level of clipping losses, which is this LC plane with values between 10 to the minus 12 to 10 to the minus 7. What we used was a criteria of imposing that the clipping losses was below 10 to the minus 8. And this is dominated clearly by the area close to the mirrors, so you can see. And then we allow for some offset in order to be sure that even if you are not totally aligned with the center of the cavity, you are not clipping much more. And then doing this basically came with the conclusion that we should have apertures at those levels I show you here, 0.84 meters for high frequency, 0.62 for low frequency. Then once you install the baffles, here you show you the tube with baffles to attract to get all the straight light, then you look at the dimensions, then essentially you arrive to the conclusion that the inner diameter of the tube should be at least 1 meter for high frequency, a little bit less for low frequency. Well, in ETCDR, essentially we impose 1 meter diameter, and this has been, of course, input into the civil engineering structures that will condition also how the tunnel will be and so on. So that's the first result, essentially, that according to clipping losses, the CDR numbers are essentially appropriate. Then we look into what would be the strategy for placing baffles inside the tube. The idea is that this is just one section close to the mirrors. So you place baffles in a way that you never see the bar tube, because you are very worried about shiny places that will backscatter immediately, and you don't want really to expose the mirror to any detail of the vert tube. Therefore, the baffles are placed in a way that you are covering completely the field of view from the mirror, from any position of the mirror. Well, if you do that, then you arrive to a number of expressions that allow you to say, once you place the first baffle, then you know where to place the other ones. And this is basically what we did. And how many baffles you need to place? Well, for high frequency 1 meter diameter, you need to play about 120 minimally. Okay, for low frequencies 90. You see a number here, which is what happens if you make the tube even larger, not 1 meter, but 1.2 meters. And the reason to do that is because we felt like 1 meter was kind of tight, and we wanted just also to give the numbers for a little bit wider. Well, that's basically what you get the feeling. In each of the tubes, you will have minimally order 100, 120, about 100 baffles. One of the things that we didn't do in this study is to attack what happened very close to the mirrors, what happened in the area of the cryotrap. We just simply started from the moment where the cryotrap ends, and then we look into the main tube. Okay, so this is more information here. Of course, according to this expression, then the baffle distances between baffles, the distance between baffles increases rapidly. So there are more baffles at the beginning, and then they get well separated. The fact is that what happens typically is that you put baffles not just where geometrically you need to put them, but also sometimes between sections of vacuum tube. And if you do that, like for example, every 50 meters, then you will double the number of baffles. This is actually happening in LIGO and Virgo, and will happen, I'm sure, in ET. Also because the baffles are used also to hide other structures inside the vacuum tube, like for example, vacuum pumps or anything that actually is attached to the tube. But I think that the message is that I gave you the minimal geometrical, which is about 100, but once you start considering that you will be placed baffles at a given point between sections, then you double easily this number. Okay, then we go into the straight line noise calculations. This is just a slide to make the note that we are using detailed analytical calculation based back in time by Leander and Virgo. We also run numerical simulations whenever possible. And the important point of this slide is that there is a number of unknowns. And therefore, we will be only happy if we see that the final noise is well below a factor of 10 merging respect to the sensitivity. So you don't want to touch at all the sensitivity curve of ET, and you want to be well below. Well below means at least 1 order of magnitude below, because there are uncertainties. So let me go into this. So what are the sources of scattered noise? So here we are considering that we are putting baffles. Therefore, basically, we don't have any problem with light going into the tube. But then in the presence of baffles, there are a number of things that happen. The first thing that happens is that the light will see the baffles. There will be a backscattering from the baffles to the mirrors, and that will produce a phase noise because the baffles vibrate, but also will have a radiation pressure into the mirrors, and this will generate noise. There's another thing, which is diffraction. So when the light goes into the edges of the baffle, then there is the potential of generating coherent diffraction noise that then pile up. I mean, it's coherent in the given baffle and then pile up for all the baffles you have and becomes an important contribution. Here we are including the phase noise. We are working on getting the pressure. I will say something about it. It's not ready, but it's basically, we are working on it. Basically, we are almost ready. I will tell you what that means in terms of result. Then there are other things that might happen, which is the thing that you might expose the edges of the baffles to the light and then come back. And if you do that, I will show you that once you decide to serrate, I will show you what that means. The baffle, then this is not a problem because basically there is no effect of piling up. Okay, so what we do is to make the calculation. We have some number of inputs. One is the optical quality of the baffles themselves, since the light has to come back from the baffle. Has the depends on the amount of light in the cavity, depends on the quality of the mirrors, and depends, of course, on the apertures, as we said. So we are using these numbers. We are using BRDF levels of the level 10 to the minus 4. 10 to the minus 4 is a standard quality of baffles these days. Of course, you can get worse, but 10 to the minus 4 is a typical number. We are assuming that things are moving, okay, and things are moving according to how the floor moves. We don't have information about how the frequency transfer factors are, the transfer factor in frequency are propagating from the ground to the structure, to the tube, to the baffle. So we are considering that the baffles move as the floor moves. So transfer factors are 1. And then we are using a simulated mirror maps. So we don't have the mirrors for ET clearly, but we have an anticipated quality in terms of how the roughness will be. This allowed us to simulate the BRDF inside the cavity. And this is the plot I show you here, where you see it's inside the cavity, so you see also the whole bin. And basically what this essentially allow you to do this BRDF. I put an arrow here because it's where everything becomes relevant. It's at large angles, okay? At very low angles, you see essentially the bin. At very large angles, you see the area relevant for the baffles. Now, we cannot extend this plot to very large angles. This is, sorry, I don't see, this is angle theta. You cannot go in a very large angle, so you cannot go like this because the accuracy of the mirror maps limit the scattering angle that you can really compute. Okay, so essentially we cannot extend. I mean, we can parameterize and extend, but according to the simulated BRDF, we cannot go well beyond. This is basically relevant, as you will see. And then I using how many baffles we are going to use in the calculations. We are going to use the ones where we put not only the minimal to shield the tube, but also once every 50 meters at a given point. So with this factor of 2 more baffles. Okay, so let's talk about diffracting noise. So, well, as I said, what happens is that when you have a baffle with an aperture, there will be a diffraction pattern coherently happening across the edge of the baffle. There will be a number of baffles, and then you have the risk of generating noise. This is the noise at a given frequency, and this is the number of baffles. Okay, so this is how the baffle moves. And this kappa is a parameterization of the BRDF in the large angles that I show you. So it goes like kappa over theta squared. So if you put this, then do generate a given noise, which is these plots are the noise for diffraction only. Then you will have the red ones. This is for low frequency, this is for high frequency. For low frequency, you start going dangerously close to the factor of 10 margin of the sensitivity. And this is for unserrated, so it's smooth. Once you place serrations, and the serration is not totally random at all, is basically the size of the valleys and the dogs to the width of the Fresnel zones. And then there is some randomness on top, okay? But once you follow this prescription, then you get expressions like this, which only is phase noise, which basically, if you put in the plot, then is the blue. And clearly you are depleting by almost 2 orders of magnitude the noise. So once you serrate, you destroy the coherence in the diffraction in a given baffle, and then everything is depleted by 2 orders of magnitude. What happens if you put radiation pressure? So photons that go too back to the mirror and push the fact that pushes the mirror, how that will change? Well, this will increase a little bit the low frequency. Okay, we are working on that, but I tell you that the plot will be a little different at low frequency. Okay, so basically once you serrate, you are basically fine. Then what about the backscattering? Well, here it is what here concerns is that the light goes into the baffle and essentially scatter back. So you need to know what is the mirror maps, and this is what I was telling you, that we have a 1-dimension PSD for the mirror quality. We have the actual description of the mirror 403, which is installed in Virgo and has been running. We have the predicted of 5, which is better. This is the measure of 3. So you see that essentially what you see here is X and Y and the height of the defects, if you wish. So you see that is much better on the center and the edges. O5 is too simple because we have only the 1-dimensional, and this you see from the difference that clearly is not totally realistic. It's a simple model, but that's what we have. Okay, so we can with this compute how much power is illuminating each baffle, and we can use an expression that allows you to say how much the backscattering actually pushes, change the phase, and also pushes the mirrors. This includes the radiation pressure, and this is basically what you do. One thing that should say is that clearly this depends on the mirror description critically. And as I said, we can only use the given angles because we are limited by the quality, what the resolution in the mirror maps. And what we do in order not to go to high angles is to use half of the baffles. So we use from this mirror only the second half, and we multiply by 2, essentially. This is an approximation, but it's based on the fact that most of the noise will come from low angle scattering. So it's affecting these mirrors and not so much the other ones. But clearly, this is an approximation, which is well motivated, because if you compute this plot, you compute this BRDF at 10 kilometers, so very far away from the mirror, or at 5 kilometers, so just here and the first baffle in the middle, then you will get the same amount of BRDF, telling you that the baffle sees more or less the same light here and 5 kilometers later. So somehow you are essentially allowed to use half of the tube and then multiply by a factor of 2. Okay, so this is the final result. I just put here the total and backscattering and diffraction you saw before. So what you say is for low frequency, everything goes 2 orders of magnitude below. And for high frequency, the same thing. For low frequency, diffraction is more important. For high frequency, everything is about backscattering. The results are very similar to the both sides. I mean, this is Euregio is close to Maastricht, and this is basically we have the same results for Sardinia. They look very similar, the same. So this is good, means that straight night noise is not a problem. But I want to say also that there are room for even improvement, right? Because you can start reducing the vibrations of the baffles by damping the vibrations or suspending some of them. And also, even as I told you that 10 to the minus 4 BRDF is a good number, you can go to 10 to the minus 5, and this will buy you a factor of 3. So you are easily reducing even this curve by a factor of 2 if it's needed. Okay. Okay, this is the first part. Let me go into the second part, which is I was talking about baffles, which looks like these things. One thing that we introduced is the concept of smart baffles, which means you don't just deflect the light and eat the light, but also you try to get a picture of how the light looks inside the cavities. This has been, I will show you what we have, but basically the idea is that if you instrument the areas in front of the mirrors, then you will be able to pre-align. You will be able to have a dynamic mapping of the mirror surface, because clearly the amount of light coming from one mirror at low angles is dictated by what happens to the mirror. You might monitor developing of higher order modes, and also very important, if you read out these things very fast, you might correlate with glitches. Okay, you see a glitch, and you can correlate with changes in the amount of light going into the cavity at a given moment. This was very challenging because required sensors of infrared sensors, ultra high vacuum. This everything is hanging by a couple of wires, so it's no cooling. We need to keep the optics healthy, so it's very small reflectivities, no much scattering, and we explored to go wireless in a way that we limited the number of cablings in order to read out the device. And of course, we don't want to pollute the payloads and the suspension feedback throughs, so there should be non-negligible electromagnetic noise. Okay, so we installed a demonstrator in Virgo in 2021 that works. So I want to show you this how it looked like, the demonstrator with a baffle, hold, and the back. Hello? Okay. I'm basically arriving to the end. So we built, this is the demonstrator, and basically conceptual design is to have whole baffle in the back sensors with PCB, and there was a lot of things to do in a way not to increase the scattering. This was also required a new sensor for Hamamatsu, because these sensors Hamamatsu off the shell will reflect 50% of the light. So there was an R&D together with Hamamatsu to go into the level of 1% reflection, and this was done, maintaining the linearity, and that was done. And we have sensors that basically are linear where they should be linear, and they have a reflectivity which is at the level of 1.something%. We tried to do better below 1%, but then we were basically killing the linearity too soon. Okay, these are nice pictures to show you how the thing looked like at the time of installation. This is the baffle coated with the holes. These are the sensors, which are also coated. The PCB with electronics is gold, totally golden, because it's a way to spread the heat without need to do cooling. We installed it in April 2021. We have been running this since then, so it's more than 2 years. It's working, it's not affecting the cavity, and everything looks good. And then we compare the information from the simulations. The same simulation I was showing you has been used in order to see whether we can follow up what the detector tells us, which is dominated by what happened with in the mirrors in front of it in the input mode cleaner. And that's basically, this structure is dictated by the roughness of the input mode cleaner mirrors in front of this, on the sensors. Okay, so this is basically the same demonstration works. Now we are building big ones. Big ones means 1 meter, almost 1 meter diameter, with much more sensors, 120 sensors. And the idea is to go very fast, 1 kilohertz. And well, this is basically working. Now we are working on that. And I show you some pictures here to see. And we did some simulations to see how to show that these baffles, one installed, can be used to pre-align the cavity. And the figure that you can take home is that we are able to pre-align misalignments of the level of 0.8 microradian. So it's not super precise alignment, but for pre-alignment works very well. Okay, so we also make some work on whether we will be able to see point absorbers in the mirrors, and it's the case. And also that we have large sensitivity to optical characteristics of the mirrors. So we start having different roughness and different level of scattering, then the baffle will immediately see it. And as I said, since we are going to run 1 kilohertz, the aim is to really correlate with glitches, which typically the duration is at the level of more than that. So you can see if the glitches comes from changes in the cavity at a given point. Okay, this is all I have. So I show you preliminary work on the scattering noise, which is almost concluded, but let me put it preliminary still. One thing I should remind is that we just focus on the main tube. There are delicate areas close to the mirrors and cryo traps that we didn't touch yet. But the conclusion is that scattering noise is under control. There is a number of approximations that has been put, and will not change the conclusion, like the fact of the pressure noise in the diffractive part. One thing that we are doing now is to compute non-ideal scenarios, for example, beam losses, point absorbers, and see whether the conclusion is the same. I believe it is, but we are going to conclude the work. And as I saw, there is an optimization to be done at a given point, because you can suspend the baffles, you can reduce the, improve the quality of the surfaces, but also you need to link this with the vacuum system to understand exactly where you need to put the baffles to hide the structures inside the tube. And also show you the work done with instrumental baffle hardware work. The idea is that this is really opening the field of active monitoring, and we are thinking on how we are going to do in ET 10 kilometers arm to pre-align, and that's the way to go. And then one last thing to say is that we are opening now a collaborating effort together with Comic Explorer on the same thing. Thanks.
Thanks, Mario. Is there any very urgent question? Because I'm afraid you already used up the question slot with the talk. So if there's one urgent question, we can do it now. Okay, there seems to not be anything very urgent. Otherwise, just contact Mario offline if you would like to discuss later on. Okay, sorry. Yeah, thanks. So according to schedule, we should have a 10-minute break now, but I suggest we skip that to get back into our schedule and make up for the delay we had at the start. So I suggest we just continue with the next talk now. And our next talk is by Meenakshi Mahesh. And there you are. Hello.
Hi.
And you will be talking about the status of compact optical heads for test mass readout with deep frequency modulation.
Yes.
Okay, yeah, we see your screen. Thanks.
Yeah.
So just go ahead.
Yeah. So good morning, everybody. I'm Meenakshi Mahesh, a PhD student from Dr. Oliver Gerberding's group from University of Hamburg. Today, I am going to talk about our work on developing a compact balanced readout interferometer using a technique called deep frequency modulation for the test mass readout in future gravitational wave detectors. So as all of us know, the future gravitational wave detectors want to achieve a higher sensitivity at this lower frequencies. And the graph on the right shows that shows the expected sensitivity that the ET should achieve compared with the sensitivity of LIGO and Virgo. And you can see at the lower frequency, we have to achieve a considerable sensitivity. And what we can do is to reduce noise sources associated with the seismic isolation and control. As we know, the large mirrors that we use in our gravitational wave detectors are suspended using pendulums, and these mirrors are actively monitored using sensors to have a and currently we are limited by this sensor noise, and to one approach to overcome this is to have a improved local sensing using a more precise sensor, local sensor. And once we have this precise local sensor implemented around this mirror, we have this sensor noise reduction, and we have a improved control over this overall mirror motion. And once we have this, we also can reduce the noise in active seismic isolation, and also we can actively damp the pendulum modes. So we are planning to implement such a sensor, and we have these sensors have to have certain requirements. For example, this sensor we have to implement around the mirror, so they should be very compact so that they will not hinder the incoming beam or will not add any weight to the test mass, add any additional weight to the test mass. And also they should have high dynamic range and multi-fringe readout capability, and the readout noise should be below 1 picometer per square root of hertz for low frequency between 0.01 hertz and 100 hertz. And we want to implement at least 6 sensors, at least 6 for the 6 degrees of freedom around this mirror. So they should be very scalable to implement dozens of sensors around this suspension. So the technique that we use to develop this sensor is deep frequency modulation. In deep frequency modulation, we modulate our laser beam with a strong sinusoidal signal, sinusoidal frequency given by omega DFM, and this omega 0 is the mean frequency, and delta omega is the modulation depth, and this omega m is the modulation frequency, and phi is the modulation phase. And the beat nodes are generated from the interference of 2 homodyne beams as shown in the figure in the right, and they have a time delay due to an intentional arm length mismatch. So once we have the signal in the photodiode, this photocurrent is given by this equation IT, and you can see on the right top how this signal will look like in an interferometer for a modulation depth of 6.28 radians for different interferometric phase. And this signal can be described in a Fourier domain by harmonics of modulation frequency using Bessel functions that you can see in the figure below, which shows this characteristic harmonics of the DFM signals, and a nonlinear algorithm is employed using this harmonics to extract the fundamental parameters like amplitude, modulation depth, modulation phase, and interferometric phase from the signal in real time. So next, I am going to discuss why we are using this DFMI for our sensors. So this DFMI technique enables us to use a large number of optical heads, as shown in the figure below. We can connect a large number of optical heads to a single laser, and this laser frequency noise will be common to all, so it will be very easy to cancel. And the fiber length noise is common mode between 2 beams in each interferometer, and that can also be strongly suppressed. And the optical layout for the readout setup requires only an optical head that is placed at a distance of 5 centimeter. So only a small distance difference in distance we need. And the past DFMI experiments also have achieved a displacement sensing level of 230 femtometer per square root of hertz around 300 millihertz that you can see from the graph below, like this graph, and a tilt noise readout with sensitivity of about 20 nanoradians per square root of hertz at 40 millihertz, and it's shown in this graph. So this DFMI technique is really helpful, and this is a sketch of the readout system for DFMI. The modulated beam is passed to a fiber splitter, and then one of the beam is given to a reference interferometer, and the others are given to the optical heads. And an optical isolator is also present, so that it ensures that no light is going back to the laser, and a phase meter is also connected. It will enable a DPM kind of readout algorithm for extracting all the parameters from each of these optical heads. And one of the other feature is that the DFMI works over different distances. Here we show a example for 10 centimeter to 1.1 meter. In the first plot shows the harmonics of DFMI for 10 centimeter, and you can see when it changes to the second figure, we have a small distance increase of 1 micrometer, and you can see how the harmonics changed. The modulation depth is almost the same, M is almost the same, but the phase changed. So we can use this phase change to employ a precise readout. And for a larger distance like 1 meter, the modulation depth changed considerably, and also the number of harmonics. So this can be used to identify larger distance and precise readout. And we can use this for precise readout. And and coming to the design of our optical head, we are using an on-axis optical head design using a collimator and a quasi-monolithic component, QMC. And this quasi-monolithic component comprises of a polarizing beam splitter, a quarter wave plate, and a beam splitter cube with a 50-50 reflectivity surface at its diagonal. So you can see how small this QMC is. It is only 11 millimeter long. You can have a feeling when it is compared to my finger, and the whole setup is less than 5 centimeter long. And this QMC basically works with polarization, and it has two outputs. So the polarization beam, the beam diagram of the QMC using polarization is shown in the right top. So the incoming beam will pass through the polarizing beam splitter. It will be completely p-polarized and then passes through the quarter wave plate. Then it will be circularly polarized and reaches this 50-50 surface. Then one half of the incoming beam will go to the high reflective surface at the back of the QMC, and the other half will go to the test mass. And it will reflect from the test mass and come back to the 50-50 surface and interfere with the beam that is coming back from the reflected surface at the back of the QMC. And we have one interference signal there, and we get an direct output there. And half of this interference signal will go back to the PBS through the quarter wave plate, and now it will be completely S polarized. So it will get reflected out from the PBS, and we will get two outputs. So if the polarizations coatings are perfect, then there will be no beam going out. And you can see the QMC act as an unequal arm length Michelson interferometer. And the precision goal we are aiming is 1 picometer. And as I have already said, our QMC is an on-axis design, and this on-axis design usually suffer from ghost beams created by the reflection from the perpendicular surface. You can see some of the ghost beams that can have like some of the potential ghost beams, but they are if the coatings are perfect, like they are very negligible. But like you can see how this beams have same effect on both the output. So by using a balance detection method, we can cancel these ghost beams. That is the advantage of using this dual readout. Like we have this dual output, so we can almost eliminate almost all the ghost beams using in post processing. So that is why we have this two outputs. And coming back to the design, we need to glue the collimator and the QMC. So we need a platform, and we call this platform a carrier. And we are planning to fix this platform, this carrier, into a 1/2-inch mirror mount to simplify the alignment during the deployment. And this platform is made of titanium because of its low thermal expansion. So then for gluing, we use two type of glues, 2-component epoxy and UV glue. The 2-component epoxy is used to glue the collimator to the carrier, and the UV glue to glue the QMC to the carrier. And both of them are expected to be low viscous for the ease of application and low outgassing, because we are expected to use it in vacuum. And also the beams should be, the boards should be strong so that it will stay longer. And currently, for the first prototype, we are using the 5-minute epoxy and NOAA 81 from Thor Labs. Now, gluing QMC is one of the critical thing in making this prototype. This QMC should be aligned to have maximum contrast because no adjustment is possible post gluing. So this QMC should be aligned in two angles, one in the plane of the carrier and one in the plane normal to the carrier. And we use an adjustable test mask during gluing. And for the alignment in the plane of the carrier, we use a controller A and B to move it in the direction of in the plane of the carrier, and a controller C to adjust it in the plane perpendicular to the carrier, and the controller D is used to hold the QMC in place. And the below figure shows how the setup will look like in an optical table, and we have done this and we have achieved a contrast of 94%. And this is how the whole setup looks like in our lab. You can see the small QMC here and the controllers, and also and the prism is used to separate the outputs so that for the ease of separating the signals, and we have the photodiodes here. So this is how the setup looks like, and this is how our first prototype looks like, and we named it COBRI, Compact Balanced Readout Interferometer. And this is our COBRI in a 1/2-inch mirror mount, and it includes a photodiode holder with tilted diode so that no beam is reflected back, and the additional lenses are glued onto the QMC to focus the beam into 1 millimeter diodes. And as I have already said, we have achieved a contrast of 94%, and the production is repeatable and reliable. So, and current investigation of the signal from the QMC made us understand that the current QMC sample has a non-ideal coating at the central beam splitter, because instead of the 50-50 coating for both polarizations, now we have an 85-15 for S and P respectively for transmission. That means the coating is polarization dependent, and the phase of the transmitted polarizations is not perfectly matched. So this means we might have some back reflection, and also the DFMI signal from the COBRI contains an unexplained envelope. This may be due to this this may be due to this non-ideal coating or some ghost beams that we can unexpected ghost beams. And to overcome this, we are now planning to order a new set of QMC with correct coatings, and also I am currently working with a more detailed model of the QMC to identify other sources of ghost beams that might cause the envelope. And in future, we are planning to test the sensor for performance by comparing 2 or more sensors and integrating this COBRI into FPGA-based multi-channel phase meter, which is currently in development by our colleagues, and making some more iterations of COBRI, and make a pendulum suspension system to test the sensor in vacuum. And the figure below shows how this pendulum suspensions looks like, and the figure on the left shows our nice big vacuum chamber, which named as Vatigraph. Yeah, thanks.
Thank you very much. Do we have any questions for Meenakshi?
I'm still unmuted. Okay. Hi there. Yes. Thanks for your talk. Just a very quick question. What is the sort of dependence on the collimation? So of course you put your compact unit at the output of a fiber collimator, but of course sometimes fiber collimators aren't so collimated, shall we say, in the output. Do you see effects from like the mode mismatch coming back from the reflection?
Currently, like, we don't have any reflections coming back. So,
okay. Oh, sorry. Yeah. Okay.
Yeah,
so there is no test mass at the moment in your setup. Okay.
No,
sorry,
we have the test mass, but we don't have any reflections going back to the laser. So we have only have it in
the.
Oh,
no, not going to the laser. I mean, like, so you have your interference signal.
Yes.
Going to your photo detectors, but
yes,
because you have an arm mismatch interferometer that relies on your collimator, basically to maintain your spatial mode, to maintain overlap as it goes back to the photo detector. Do you see any effects of like mode mismatch?
No, currently we are not facing any problem like that. Yeah, our beam is perfectly collimated, and it's only 1 millimeter long, 1 millimeter in diameter.
Okay. Right. Yeah. Thank you for the answer.
Okay. Thank you.
Any other questions? Okay, seems not. Then thanks again, Meenakshi, and then we will.
Thank you.
Then we will come to our next speaker, who is Disha Kapasi, who will be talking about measuring thermal noise in gram scale silicon flexures at 123 Kelvin.
Hi, thanks so much. I'll just check if the transition works. Yes. Hi, I'm Disha. I'm a final year PhD student at the Australian National University with the Center for Gravitational Astrophysics. And I'm in my final year. And for the past 3 years, I've been working on thermal noise measurements in silicon flexures at 123 Kelvin. So the thermal noise, the power spectral density of thermal noise depends on two things. It depends on the temperature and low loss materials. So by lowering the temperature and using niche materials like silicon and sapphire, we can reduce thermal noise in future ground-based detectors. The motivation to do with silicon is because there is a zero thermal expansion at 123 Kelvin and 18 Kelvin. So if you're operating your detector at 123 Kelvin, your linear thermal expansion goes to zero. And by virtue of that, the thermoelastic noise in substrates and will go to zero. Also, silicon has high thermal conductivity as compared to fused silica, which is currently used in the detectors and has low mechanical loss. So the motivation for this experiment is to design a cryogenic infrastructure where we can measure the broadband thermal noise in silicon flexures, which is analogous to understanding the suspension thermal noise in silicon ribbons. And to the best of our knowledge, we've not seen such measurements done before. So this is an experiment to directly do this. So the flexure design is basically motivated by Voyager suspensions. So if you look the figure on your right, this is the last two stages in a Voyager design. So that is the monolithic silicon ribbons over here, which is suspended from the silicon blade springs, and that is bonded to your penultimate test mass. This entire ensemble suspends your final test mass. These silicon ribbons over here are about 10 millimeters width, and the thickness is about 500 microns. So to test something like this, we've basically fabricated silicon flexures that you can see on the left. So they're about 500 microns thick and about 15 to 20 mils tall. And it has a mirror on one of the sides to form an optical cavity. So the mechanical frequency of this flexure, of course, depends on the thickness, the geometry, and the surface finish of this vertical cantilever. And we've tried to design our flexure to be dominated by structural loss. So the two main contributing factors of thermal noise in our experiment is structural loss and thermoelastic loss. Structural loss basically arises in the bulk of the material, kind of like in the internal friction. And for thermoelastic noise, it is frequency dependent and arises from localized heat flow, which leads to deformations. This experiment, basically to calculate the noise budget, we use the fluctuation dissipation theorem, which relates the dissipation of a mechanical oscillator to its thermal fluctuations. So equation 1 basically gives this the power spectral density. And over here, phi k is basically the total loss, which is the sum of your structural loss, thermoelastic loss, your gluing loss, clamping loss, everything else. And we have a room temperature paper that discusses the results from a silicon cantilever that you can see over here. But moving on, so this is basically the noise budget that shows for a 325 micron flexure that's in our experiment. So the graph on the left is basically that shows the loss, and we show over here the structural loss and the thermoelastic loss for a 325 micron silicon flexure. And if you convert the loss into a displacement noise, this is what the noise budget would show. The key takeaway from this graph is that what we're trying to measure at the audio band frequency where ground-based gravitational wave detectors are sensitive, we need to have an apparatus that can measure displacements at the order of 10⁻⁻16 meters per root hertz. And the challenge is to set up such an environment. So this is the total noise budget. It basically includes the contributions of mirror thermal noise from your PZT mirror, which is one of the mirrors in the test cavity, and then your silicon flexure as well, and what are the other sources of noise, such as gas damping, PZT noise, and the overall sum of that noise. So the experimental setup to test this and measure thermal noise in silicon flexures basically includes two cavities. So we have a reference cavity over here, which is used for laser frequency stabilization. And this cavity is about 20 centimeters long and has a finesse of 6,000, and undergoes PDH locking. For the test cavity, we have a short cavity, which is just about 1 centimeter. And you can see here, there's an input mirror, which has a PZT, and then this is our flexure over here. And it's a 1 centimeter cavity that sets in a cryogenic environment. So it's surrounded by a lot of radiation shields and has its own separate vacuum tank. And we have different flexures that we've been testing. Some of the flexures, like the previous one was around 300 hertz. This is around 800 hertz. So we can quickly test different flexures as well. So how does the test cavity come together? So this is the short test cavity. So the PZT mirror is mounted on a stainless steel mount, and the silicon flexure basically assembles to this aluminum base, and both of them are mounted on this common breadboard that suspends from a multi-stage pendulum, and I'll show you pictures just in a minute. The entire enclosure is basically in like a box to increase the surface area for radiative cooling. And like I mentioned, we need an environment that can measure 10⁻⁻16 meters per root hertz. So our entire cryogenic setup is radiatively cooled, and to cool it faster, we've basically increased the surface area of our test cavity. So on the silicon flexure itself, on the front side, we have resistive heaters to give us the bandwidth to raise the temperature all the way from like 90 Kelvin to like 200 Kelvin to make like temperature dependent measurements. And on the back side, we have a silicon diode whose footprint is less than 1 millimeter, and it's glued very close to the flexure, so they help us maintain a thermal PID loop. And this entire enclosure looks gray because it is anodized aluminum as well. So the entire cryogenic infrastructure looks something like this. On the right is the actual diagram of the suspension stage. So this complicated suspension system was built by Bram many, many years ago. But at the end of this suspension stage, which you can't see right now, at the end of the fourth suspension stage, we basically, as a part of my PhD, was to commission this cryogenic infrastructure. So we have 3 radiation shields over here that sit on a support structure. So it's completely decoupled from the pendulum. So it doesn't introduce any mechanical noise into our measurement scheme. So the last stage of the suspension system basically has 2 posts from where the test cavity is suspended. The innermost shield is connected to a copper chain, which connects to the cryostat, and then via a remote head connects to the compressor, which is in the plant room to remove any other vibrations and noise. The other thing is we have a copper braid over here, which also reduces the mechanical vibrations from the cryostat into our experiment. And we have a large copper bar, which weighs about 25 kilograms. So these are some, and then this is the test cavity over here. And just like optics for routing the input beam and the transmission beam, This B is where the cold head that's in this picture, the copper bar basically comes and attaches to the innermost radiation shield, and then everything is radiatively cooled. So this is the concoction for your copper chain. So there's a copper bar that connects to the braid, which then connects on the top to the cryostat. Some more pictures of the commissioning. So this is our cryostat, and if you look it from the flange that's behind it, so over here, you'll see this copper braid that's connected to a spacer, and on the other side, it's this copper bar that connects to the shield. And this is the other side. So this is how our test cavity looks when our copper bar and everything is assembled and about to be closed. So these wires are for readout. So it connects to the resistive heater and to the silicon diode for temperature measurements. And this is a close-up view of our cavity. And we use 2 mirror finished stainless steel clamps to basically clamp the silicon flexure to the aluminum base. So these were one of the first results that we did to just test our heating and cooling capability of this infrastructure. So it takes about 40 hours to go from 300 Kelvin to 120 Kelvin. And you can see over here at the different segments where we've implemented PID control to stably hold the temperature at, let's say, 105 and 110 Kelvin. And in matter of 30 minutes, we're able to shoot up our temperatures by 50 Kelvin. And if we wait around for another 30 minutes, it stabilizes the entire environment to allow us the capability to make temperature dependent measurements very quickly. And the heater that's installed on the front side of the silicon flexure gives us the capability to make these measurements from around 90 Kelvin all the way up to 200 to 50 Kelvin. The other advantage of this entire setup, if I just go back here, so we have this copper bar that I mentioned. It's about 70 centimeters long and weighs about 25 kilograms. So it's a huge thermal mass, which gives us the advantage of turning off all our cryogenic pumps and equipment to make actually low noise measurements. So it holds the temperature around 120 Kelvin for about 10 hours, before which we need to turn back our cryogenic compressor and then cool down again. So these are some thermal noise measurements that we've made. This is from a 325 micron flexure. The blue trace is the room temperature measurement, and then the cold trace is at 170 Kelvin. Unfortunately, we couldn't go all the way down to 120 Kelvin with this one because we just lost light as we were cooling down. And when we opened the tank, we realized that one of the mirrors had fallen off. So our best measurement was at 170 Kelvin for this one. But then after that, we've done a couple of upgrades to the experiment. So we started fabricating silicon samples within the department with the idea of making it like having the edges more smoother instead of laser cutting it. So we used a diamond tool to cleave the flexures, and then we prepared the surfaces using dry nitrogen gas and wiping it with optical grade methanol. And then we started bonding 2 different pieces of silicon, and the motivation to bond them is to reduce the clamping loss that can come between the 2 stainless steel clamps and your flexures. So if you increase the base and keep a ratio of 1:5 or 1:10, then you would minimize the loss that can go into the clamp. And then these bonded samples were annealed at 575 degrees for 10 hours. And then the motivation was to basically put IBS coatings at the end of these cantilevers here that you can reduce even the mirror loss and any glowing loss that can contribute to this experiment. The other thing was the previous setup where in the 325 micron flexure, we had EBS coated mirrors, and we had trouble keeping up with the light because the finesse kept degrading. So we've then moved on to IBS coated mirrors. So at ANU, we have the Australian National Fabrication Facility, and Johannes is a part of that. So he and his team helped us basically put silica tantalum 1064 IBS coatings on our cavity optics itself. So we ordered the substrate, and then as you can see over here, this is the flexure mirror that's being mounted into our into the IBS coater. And we had to make custom mounts for this to account for the radius of curvature difference between the PZT and the flat flexure mirror. And then they both went into the same run. And now we use the IBS optics in the cryogenic experiment. Lastly, these are one of the latest results, and I'm still analyzing it. So this is from the 1 kilohertz flexure that we made in-house at ANU, and has the IBS coated mirrors on it. So the blue is the displacement noise at 123 Kelvin, and this is the off-resonance noise, and then this is the noise flow of our experiment itself. We're still trying to understand what these multi-peaks below the resonance are. We've tried to eliminate these 4 things. So one is the PZT noise. So we have a high voltage amp that supplies the voltage to the PZT with the low bandwidth servo. So to eliminate this, we basically took off the high voltage amp and used the laser to just bring it on resonance and make measurements. To eliminate laser frequency noise, we made the measurements in our reference cavity, and they didn't have similar structure. For the environmental noise, the entire vacuum tank sits on 3 legs. So we basically just put a force on one of the legs it sits on, and even used a hammer to bang the tank, and those modes just didn't disappear. And the last is to turn off our cryogenic pumps and the vacuum pumps for this experiment. So none of these contribute to that, but this is still a mystery, and we're trying to understand this. And this is the last slide. So right now we are writing a cryogenic infrastructure paper, which covers the details of this entire infrastructure and the capabilities we're able to reach for measuring thermal noise in silicon flexures at 120 Kelvin. We're also redoing the direct bonding of silicon strips, or will be doing, hopefully, bonding of silicon strips to the base, because the success rate was really low. For every 10 samples we put in, maybe 1 would come out fine. So we need to come up with a better strategy to get more samples out from the bonding experiment. Moving on, the next part of this, the upgrade to the experiment would be to directly apply IBS coatings on the silicon flexure itself to replace the mirror, which eliminates the gluing loss, and that's a future upgrade. And lastly, just finalizing some noise budget to make sure that I've incorporated everything for the measurements I've been making, and hopefully I'll be done with my PhD in 6 months. Thank you. Happy to take questions.
Thank you very much. Do we have any questions for Lluisa? Jan, please.
Hi, Lluisa. Thank you for your talk. Please, I didn't catch for which detector it is this machinery used? It is for ET or for Cosmic Explorer, or for which? I didn't get.
This is motivated for LIGO Voyager currently, at least like the size and the geometry of the flexures that we're doing was just motivated by LIGO Voyager when I started this experiment.
Okay, thank you.
Any other questions? Seems not. Then thanks again, Lluisa. And then we will continue with our next speaker, who is Jennifer Wright, and she will tell us about commissioning of the torpedo suspension chain.
Okay. Hi, everyone. So you've already maybe heard a bit about it, but I'm going to talk about the torpedo detector, which is a Newtonian noise detector that we're developing at Australian National University. And right after my talk, Avnish will give another talk on the same experiment, but his will be about the laser frequency stabilization for the experiment. And so his is more optics focused and mine is more suspension focused. So yeah, these are some of the people who are involved in this work, some previously at ANU, some currently at ANU. So if we go So yeah, the motivation behind this is that the next generation of gravitational wave detectors will be limited by Newtonian noise below 20 hertz, or we expect it to be. And there are several ways that people have already come up with for getting around this problem. So one thing you can do is you can measure the seismic noise near your detector, and you can model the Newtonian noise you would expect from that and subtract. So you can just model it entirely, or you can measure the seismic noise, and then subtract what Newtonian noise you would get from that. But Newtonian noise is caused by density changes, which alter the local gravitational field, and this produces this noise in the detector. And I've mentioned you can subtract its effect afterwards, but you can't shield the detector from gravity, from the very changes that we're trying to detect with our interferometers. So if we could have a direct detection method for Newtonian noise itself, this would be very interesting. And down the bottom here, I have some references for these kind of other efforts and other methods. Okay, so the principle of the torpedo detector is its two torsion pendulums. So assuming these animations run, this is on the left is like a top-down view of the two torpedo bars. So they're kind of independently suspended. So the blue one is one and the orange one is the other. So if I just run that, it shows what happens if a mass passes along the side of the detector. And then this one on the right shows what would happen if you got a density change in the environment of the detector. And obviously this is very unphysical, so you should just think of this as a density change and not something magically getting bigger and then smaller. But yeah, thanks to Dion for making these animations. So there is one thing that you may have realized with this is that there's a certain detector pattern that each bar sees. And so there is a degeneracy between a mass moving from one side, moving inwards from one side, or moving inwards from the other. And you can sort of solve, or you can make your kind of detection of Newtonian noise kind of more accurate, provide a more accurate map of it by combining several of these detectors together at your observatory site. And so you can combine them in different orientations to get around this. And also you would probably want some of them near your detector and some further away. So you get the Newtonian noise due to local effects and Newtonian noise due to things happening further afield, because it's not just seismic noise that might cause these density changes. You might also get anthropogenic noise, like in the near field, like really near your detector, and you can also get infrasound causing Newtonian noise. Oh, yeah, there we go. Okay, so this experiment, I think, has been sort of building up in stages for about the last 10 years at ANU. And so Nathan Holland and some others got a controls prototype working. And this was the two torsion bars, but this was in air, and it was not suspended from a multi-stage suspension like the current torpedo. And so that meant that there were some limits to how sensitive the measurement could be, because the suspension point was not still enough, basically. But the readout works well. So yeah, I'll talk a bit more about that in one of the next slides. But basically the idea is we needed a more complicated suspension system, and we needed it to be in vacuum as well. Okay, so this is a paper that we published recently, and this is just updating some of the theory that we're kind of operating, that we're trying to achieve experimentally in the lab. So we measured the seismic noise in our lab, and then we predicted the level of noise we would expect for seismic body waves in this dark green one here, and seismic Rayleigh waves in this yellow trace here. And then the thermal noise from our suspension system is shown in red here. So this is kind of the limit, or one of the limits, and our shot noise is the other limit, and that's the dark blue line along the bottom. And so, yeah, the seismic Rayleigh waves, the seismic body waves, and also, sorry, it's the Newtonian noise level due to seismic Rayleigh waves and seismic body waves, and then also due to infrasound in this kind of muddy green color here. And then we also injected a calibration tone to check that we would be able to see a signal, and this was done, so this is done theoretically, but it's basically using a model of a Newtonian calibrator as if it was next to the detector. Okay. Yeah. So this is a picture of the torpedo from SolidWorks, because it's kind of clearer to see than a real picture from the lab. And so this table-like structure is sort of connected to ground. So this kind of sits in the tank here. And then the first stage is a multi-SAS system. And this is similar to, I think, the first stage of seismic isolation for the Virgo optical benches, and it was made by InnoSeis. And so this consists of an inverted pendulum. So it has one leg here, and one around the back. So it's just like a table with wobbly legs, basically. And hanging from the top of this inverted pendulum is a geometric anti-spring, and this is kind of a ring of blade springs. And then at the middle of this ring of blade springs, we have a single thing which we call a keystone, and from that hangs our intermediate mass, which is this weird looking gold thing you can just see in the middle here. And then from the intermediate mass hangs our penultimate mass, which has these little like bun ear type things sticking out at the side and at the top. And that's just hanging below the structure here. And then we have our two torpedo bars hanging from the penultimate mass. So there's a single wire between the geometric anti-spring and the intermediate mass, and a single wire between the penultimate mass and the intermediate mass and the penultimate mass. And then we have two wires for each torpedo bar hanging from the penultimate mass. Okay, so this is not a very clear picture, but this is what the multi-SAS looks like in the lab. And so we had to do some commissioning, because once this was all assembled in the tank, it's very important that the top of the inverted pendulum is level, because if it isn't level, the system becomes unstable and it can kind of fall over. And so we have some sort of adjustments that we can do on this base plate here. And this is to kind of level the top of the inverted pendulum. And then after you've done this leveling, you also need to slew the top of the inverted pendulum round to ensure all the legs are standing upright. And this is because you can get some kind of yaw offset as you're leveling it. And we do this, we have some stepper motors that can kind of swivel around the top of the IP. Okay. So yeah, this is just kind of simplified layout of the IP and the geometric anti-spring. So yeah, as I've said, this is kind of a side view. So these blue things here, these are the blade springs. This thing in the middle is the keystone. And then there's the suspension wire hanging down to the lower stage. And And yeah, you can see the IP legs, they're kind of thinner at the bottom. So most of the bending kind of happens at the bottom of them. Yes, and on the left here, we have sort of a picture looking down through the inverted pendulum at the ring of blade springs. And you can see on this keystone, we actually have a relative position sensor to sense the vertical motion of this keystone. And basically the design of the multi-SAS is meant to kind of ensure that your horizontal degrees of freedom are decoupled from your vertical degrees of freedom. So we want the sensor on this keystone to just sense vertical, and then we have 3 of these relative position sensors on the top of the inverted pendulum, and they should just sense horizontal. Okay, so the intermediate stage, you can see a clearer picture of it on the left here, and you can see the penultimate mass more clearer on the right here. And you can see they both have these kind of symmetrical designs, and actually you can slide in these disks into the center of the intermediate mass, and you can move in and out some of these disks on the penultimate mass. And that's because for the modes we get of the whole suspension structure, it's very important that we have some tuning on the moments of inertia, because the measurement we're making for the torpedo bars is like a sort of a relative torque measurement. So we're trying to make sure that we don't have any unexpected torques anywhere, so we get a very clean measurement. Okay, so this is the bottom stage, the torpedo bars. And I mentioned that we were looking for this kind of rotation measurement. So we're looking for basically the angle between the bars to change. And the way that we monitor that is we have 4 optical cavities. So there's the bar there, and then we have these cavity mirrors just sort of at 45 degrees on the ends of the torpedo bars. And so that means we have 4 resonant cavities, and we use those to monitor the bar rotation. And you can see we also have some mirrors on top here, and we use these to sort of monitor the alignment of the torpedo bars, like kind of to see if they're tilted or not, because we can shine some other lasers down and use these for optical levers. And then we have our 4 suspension wires connected to each of these red things at the top of the bars. And the design has these kind of ballast masses on it. So one bar has 2 on top, the other bar has 2 underneath, and this kind of ensures that they have the same common center of mass, basically. Okay, so this is a simplified version of the readout. And so I'm sure you're going to see slightly more complicated optical diagrams than this in Avinesh's talk. But yeah, so each bar or each bar end has an optical cavity between it and the next one over. And each of these is locked using Poundry-Hall feedback. So that's just a representation of it here. So yeah, we just have some sidebands on our laser that we use as a reference, and we do some demodulation and we get a signal. And then you combine those 4 signals in order to get this relative angle measurement, basically. Okay, so we've done quite a lot of commissioning efforts in kind of the last couple of months. So on the left here, this was us kind of doing the final installation of the torpedo bars. So we had all the other stages of the suspension built, and we just had to hang the torpedo bars. But before we did that, we actually had slightly the wrong length of suspension wires from the next stage up. So we had to do some reclamping of those wires. So that's what is pictured on the right. But yeah, so as of this month, all the stages are free hanging, and stuff's looking good. So we're just kind of moving down the stages and commissioning the different parts. Okay, so this is just a slide about some of the problems we've been discovering during this. So when we had everything free hanging, we noticed that our torpedo bars are not oriented as they should be in the sort of rest position. So they should be at 90 degrees. And there is some kind of slight offset angle that one of them is kind of hanging at. And so we're moving through a series of kind of engineering solutions to try and work out how to correct this. So one option is we can sort of find out some way of applying a static torque between the bar and the wire. So we put some kind of angled spacer in that holds the bar slightly at an angle to the mounting or the clamp at the bottom of the wire. So that's one option. And then there might be some other clever thing that we can design where we take the bars off and see if the wire clamps rotate in one plane. And then that will tell us if our problem is due to our wires being twisted or some other problem that we haven't foreseen. So yeah, we're just kind of in the middle of those efforts. Okay. And moving back up to the top of the suspension chain, this is an amplitude spectral density of the inverted pendulum degrees of freedom. So this is the horizontal relative position sensors. And we're sort of in the process of setting up the control system for that at the moment. And so you can see here at 0.09 hertz, we have a resonance, and we should see it in the transverse and longitudinal directions, but we should not see it in the yaw direction, which is this green trace here. And we do have some cross coupling between our yaw degree of freedom and longitudinal and transverse. So we're just working on some corrections to our input matrices at the moment, because we've got them set up for an ideal system, and obviously systems are never ideal. And so that work is kind of ongoing. Okay, so the control strategy for the torpedo is that you basically have two loops for each stage. So you have an inertial, so you have a damping loop that basically damps the suspension modes. And then you have an inertial isolation loop that basically acts to isolate that stage from the absolute motion of the previous stage. So with the inverted pendulum, we're measuring the acceleration. So we've got accelerometers on the top of the inverted pendulum, and then we're also measuring the relative position between the inverted pendulum and the suspension structure. And we need to combine both of these sensors, both for our isolation loop and for our damping loop. So we're kind of using CDS, so that's why I've put this picture in on the right. And so we're just kind of working to populate these filters just now. And our strategy is going to be to start with kind of classical controls and see if we can get the system damped. And then we're probably going to move on to some more complicated controls later to optimize things, but I'll talk more about that just towards the end. Okay, so the sensors and actuators, as I mentioned, we have Trillium T240s. So they're these three huge cans on the top of the IP because they need to be, they can't be at vacuum, so they need to be kind of sealed. And then here we have one of the relative position sensors. So these are LVDTs. And then those are the two sensors. And then we have voice coils to kind of actuate on the kind of vertical degree of freedom. And then on the keystone as well, we have a strain sensor in vertical. Yeah, so we have like a PZT that we can use as a strain sensor. On the intermediate mass, we've got coil magnet actuators, but Zhang was talking about optical sensors that we're developing, and we kind of hope to use these on the intermediate mass and also the penultimate mass. And that is because there's not a lot of room in our structure. There's lots of like bits of metal going everywhere. And so we've tried using shadow sensors before, and they were quite difficult to use because we kept on hitting the flags and stuff. And also the noise floor we need, we kind of need more sensitive sensors as well. So the penultimate mass for actuation, we're just using OSMs. And then the torpedo won't have any kind of in-loop actuation on it, but we will possibly install OSMs next to it for kind of pushing, just for initial alignment. Okay. So the next steps are kind of to design a blend between the accelerometers and the relative position sensors for the multi-SAS. And then after that to kind of install either digital interferometric sensors or some other kind of optical sensors on the intermediate mass and the penultimate mass. But we're still kind of, some of these are in design phase, so we're kind of still to narrow down which ones we definitely want to install. And then, as I've mentioned, once we have the system controlled, we're probably going to look at some nonlinear controls. So we are probably going to do H-infinity optimization, and we might at some point do machine learning, but we really need to look into that a bit more. So yeah, we're getting everything done in a sort of classical way first. Okay, so thank you for listening. Does anyone have any questions?
Thanks, Jenny. Any questions for Jenny? Good, so if there are no questions, then thanks, Jenny, and then we can just slowly continue to our next talk. The good news are we are back in time, which is great. Our next speaker, which is due to start in 3 minutes, so just start very slowly, will be Avanish Kuluramamohan, who will talk about characterization of heterodyne phase logging for a Newtonian noise sensor.
Hi, everyone. I'm Avanish. I'm doing PhD at the Australian National University. Jenny already gave a nice introduction to the torpedo sensor and the seismic isolation chain. That makes my talk easier. So I'll be talking about the readout part, that is mainly about characterization of heterodyne phase locking for the Newtonian noise sensor, that is torpedo. To begin with, so the future detectors, that is third generation gravitational wave detectors, such as Cosmic Explorer, Einstein Telescope. If we look at the low frequency cutoff, the plot on the left shows that it is about, for the Cosmic Explorer, about 5 Hertz, and Einstein Telescope is about 3 Hertz. So it is important to improve the low frequency sensitivity. It has a significant benefits, but we are mainly limited at low frequency by seismic noise and Newtonian noise. As you can see on the plot on the right is one of the sensitivity plot for the Cosmic Explorer. At about 5 Hertz, we see it is mainly limited by seismic noise and Newtonian noise. So yeah, so what is Newtonian noise? So basically, it can be any sort of disturbance like atmospheric disturbance, or it can be ground motions, or it can be like human activities around the test mass. So these disturbance, if it changes the local mass density around the test mass, and that causes the test mass to move, and that is known to be Newtonian noise. For example, let's say motion of this truck. So this motion of this truck introduces ground motion, and that couples to the suspension to the test mass, and that is a seismic noise. But also this ground motion will introduce a changing Newtonian attraction on the test mass, and that causes test mass to move, and that is Newtonian noise. So I'll be focusing on Newtonian noise here. So Newtonian noise, it is hard to shield the detector from this because it is a local gravitational force fluctuation. So we need a better site selection, or let's say we can, like for the Einstein telescope, it is considered to be going underground. So we can take such measures. Also, we can develop some cancellation techniques, that is by modeling Newtonian noise, or having an array of sensors to get an estimate of Newtonian noise. Or we can actually have an direct detection of Newtonian noise. So in these are the lines that we can work to mitigate the Newtonian noise. So here at ANU, we're developing this sensor, low frequency sensor, which stands for torsion pendulum dual oscillator, torpedo. So this is basically 2 torsion bars suspended. As Jenny already explained about the how the geometry works and the seismic isolation. So I'll more focus on the optical readout here. So when there is any change in the local mass density around the 2 torsion bars, they respond by a differential rotation towards the changing local mass density. And that differential angle is what gives us the Newtonian noise measurement. So that is done basically by having 4 Fabry-Perot cavities around the 2 torsion bars that is formed by the attached end mirrors. And each of these cavities will be injected by a separate laser, and the laser will be locked to the cavity by the standard Pond-Hall technique. So by having measured the cavity length changes of these 4 cavities, and with the simple geometry of the torsion bars, we can reconstruct the differential angle measurement between the torsion bars, and that gives us the Newtonian noise measurement. So more details. So this is Jenny already showed this plot about the target sensitivity. That is the black curve here is the will be the target sensitivity for the next generation torsion pendulum detector. So that is the target sensitivity is defined by the thermal noise of the suspension wires and the readout short noise. And also this plot shows the projections of Newtonian noise from various noise sources. So by reaching the target sensitivity, we aim to measure these. There is potential detection of Newtonian noise is possible. So moving on. So as I already mentioned, we're using 4 different lasers for the locking for the 4 different cavities. This is because in the previous prototype, when it was set up, we could see that the residual motion of the bars were too high, and we did not have enough dynamic range to just work it with a single laser. So with the new commissioning of the new seismic isolation chain, we expect the residual motion of the bars to be an order of magnitude lower than before. So we can consider having a single laser. But as of now, we're working with 4 different lasers, and having 4 different lasers in the readout will introduce frequency noise. That is when they're free running. As you can see in this plot, this is in equivalent frequency noise units. So the 4 lasers free running frequency noise and their quadrature sum, the green curve, is clearly dominating the readout. That is, our aim is to suppress the frequency noise below the target sensitivity, the relative frequency noise between the lasers. So for that, we have set up the heterodyne phase locking for the readout lasers. That is, we have these 4 readout lasers, and we lock the readout lasers, and we have a 5th reference laser. And what we do here is we phase lock each of the readout lasers to the reference laser. And by doing so, all the readout lasers will follow the reference laser noise characteristics, and the frequency noise among the readout lasers becomes common, and therefore gets cancelled as a common mode rejection in the differential measurement. So that is a sort of idea behind setting up the heterodyne phase locking. I'll go into the more details later. So this is a model that is showing that having set up the heterodyne phase locking for the readout lasers, we can achieve the suppression of relative laser frequency noise down to below the target sensitivity. This is the modeling we aim to achieve. That's the performance we aim to achieve. So the simple working principle of the phase lock loops here is that we beat the readout laser with the reference laser and optically, and that gives us the beat node, and we inject that to the servo, electronic servo, where we demodulate the signal, and that generates the error signal. And using the PID controls, we feed back for the slow and piezo T of the readout laser, and by doing so, we phase lock the readout laser to the reference laser. And as you can see, the local oscillator is at some megahertz. That means these 2 lasers will be phase locked, but will be at different frequencies. That is offset phase locking. So that is the heterodyne phase locking here that we are working. And on the right, you see the plot of transfer functions of different components in the phase locked loop, and also the resulting open loop transfer function. So I've set up these, so we have these phase lock loop set up. So now in order to characterize the performance of the phase lock loops, here on the right, it shows the, I've shown it in the different colors, the path, the optical paths. So for the in loop, the blue curve, the blue path shows the in loop, where the readout laser and the reference laser is optically combined, and then the beat node is feedback to the readout laser to lock it to the reference. So if we measure the frequency noise at the beat node, the in loop beat node, that will give us the in loop measurement, which gives a good estimate of what we can expect from the phase lock loop. But to measure the actual performance of the phase locked loops, what we do is we pick off the lasers from the readout laser and as well as a reference laser, and we optically combine and shine it on a different photodetector at a different place. So that is an out of loop sensor. Basically, it's out of the loop measurement, and that gives us the realistic performance of the phase locked loops. So here I show the in-loop measurements. The plot on the left, you can see the estimates for the free running laser frequency noise and the closed loop frequency noise suppression, which closely match to the modeling. And also, if we take the ratio of these two, we get an estimate of the open loop transfer function, and that also matches quite well with the modeling. These are the in-loop measurements. And so this is the out of loop measurement. So this is the actual out of loop sensing. So as you can see, the green curve here is the measured out of loop performance. That is basically deviates from the expectation below 10 hertz. So that is was quite interesting and challenging to identify this noise. So I started with a noise hunting with different, looking at the different noise spectrum of the phase locked loop, but none of these noise were really pointing to these this noise here. So, and then finally, also we could notice this noise was very common between all of the out of loop measurements, like in all the different 4 loops. This particular noise shape below 10 hertz was quite common. So looking at the long-term measurements, we noticed that this frequency noise, low frequency noise, was time variant of the environmental fluctuations. So basically, the in-loop and out-of-loop optical path lengths were affected by the air currents that in the lab. So in order to mitigate this, the in-loop and out-of-loop path was enclosed in a box, and as you can see on the in the figure on the right, so these optical paths were enclosed in a box to mitigate the air currents, and I also implemented a better loop shape for the suppression at for the higher suppression at low frequency. As you can see, this is the optical setup on the table. So this is the after splitting for the in-loop and out-of-loop measurement, the optical paths were enclosed in a box. And also, this is on the right, you see the full optical layout of what I have on the table, basically the 4 readout lasers and a 5th reference laser, and we optically combine for the in-loop and out-of-loop measurements, and those path lengths were enclosed in a box. So as you can clearly see, not all of the table optical paths are enclosed in a box. It's only basically when we split for the in-loop and out-of-loop measurements, that is where I have enclosed it with a box. So this is the result of having set up the in-loop and out-of-loop measurements. So as you can see, this is the out-of-loop measurements of all the 4 loops. And it is clearly we have achieved the frequency noise suppression below the target sensitivity. Yeah, so these are preliminary results because I have measured these out-of-loop measurements at a different time for each of the different loops. In the future, we will be getting these measurements simultaneously when all the 4 loops are running, and also the long-term measurements. So I'm planning to put these results into a paper in coming future. So in summary, the heterodyne phase lock loops are operational, and we have achieved stable locking for several days. And also all these 4 loops were running on a single MokuPro. MokuPro is a liquid instrument device. We used it as a servo for these phase lock loops. And the modeling and characterization of the PLLs have been done. And also we have reached the results with the preliminary measurements. So the future steps would be to implement this for the torpedo sensor, the PLLs, and also set up the Pond River Hall locking for the readout. And finally integrate these 2 loops for the optical readout. That is by basically the idea here is to feed back the error signal of the PDH to the local oscillator of the PLL. So it's a hierarchical loop architecture where the PLL is a dominant loop with a higher UGF, and PDH will be a subordinate loop with a lower UGF. So by this way, we can integrate the PDH loops with the PLL loops. This helps to suppress the frequency noise, and as well as get the readout for the Newtonian noise measurement. Thanks everyone. Any questions?
Thank you. Does anyone have any questions for Avinash? Good. If there are no questions, then thank you, Avinash, and then we can continue to our last talk of the session, which will be by Katharina Isleif, and she will talk about distributed seismic fiber networks and their potential for current and next generation gravitational wave detectors. So if you're ready, please go ahead and share your screen, Kata.
Okay,
Really good. Yeah, so I'm giving the talk on behalf of the WAVE initiative. It's an initiative in Hamburg. So you can see here also the people involved, or the logos of the universities. And I'm also giving this talk on behalf of Reinhard Harding. So he's a PhD student in my group in Hamburg. And he's currently on travel from another conference. So I need to give this talk now. So yeah. But I will try to do my very best. And I think it is quite easy for me today because there was already an introduction into Newtonian noise and seismic noise in future and also current gravitational wave detectors. So I will just start with a recap. I hope it is working. Yes, now. So here you can actually see the current strain sensitivity of the advanced LIGO detectors in blue. This is a measurement curve of the observation 1-3. And the Einstein Telescope design sensitivity, which is here plotted in red. And to get the sensitivity down for the Einstein Telescope, you can already see that we aim for a factor of 10 improvement over the full frequency range. And especially at low frequencies, we have a huge challenge because we want to suppress 5 to 6 orders of magnitude at around 3 Hertz. And this is really the biggest challenge for future detectors, not only the Einstein Telescope, but for example, also Cosmic Explorer. So how do we get down? So here at low frequencies, the main limiting noise sources is seismic noise or also control noise. So what we do is we build newer passive isolation systems, like for example, the advanced super attenuator, the advanced Virgo super attenuator, where we need to improve the length from 9 to 17 meters. And we have also learned today by the talk of Meenakshi from the University of Hamburg that we need novel sensors to get rid of seismic control noise at low frequencies. However, if we are able to improve these systems, the active and passive seismic control, there's a new noise source which is coming up, which was just introduced by my pre-speakers, which is called Newtonian noise. And here at low frequencies, you can see a simulation which was done by Jan Harms in 2015, where you can see the impact of seismic surface waves on the Einstein Telescope. So this is now not seismic noise, but it's Newtonian noise. So here on the right, you can see again how Newtonian noise couples due to density fluctuations in a body or the Earth. And you can also see that the surface waves can be suppressed if you go underground. Like it is here shown for minus 700 meters, you can get rid of Newtonian noise from surface waves. But you can also see that the body waves still limit the Einstein Telescope sensitivity at low frequencies. And this is something that cannot be suppressed if you go underground. So what we can do to get the Einstein Telescope sensitivity in the end, we need a really careful seismic site characterization, which is currently ongoing. So we measure the seismic noise at different sites, and we need a location which is, of course, as quiet as possible. Next step would be to go underground, which is also the plan for the Einstein Telescope, to at least suppress surface valley waves and also atmospheric waves. So not only seismic is producing Newtonian noise, in principle, any density fluctuations produce this kind of noise source. And in the end, because we are still limited by body waves or some residual Newtonian noise, we need a Newtonian noise cancellation system to get rid of it. And how such a system works is just depicted here. So this is actually the basis for all coherent noise cancellation techniques. So you have an experiment here, for example, a gravitational wave detector, which produces gravitational wave data which is noisy. So here it is, for example, limited by Newtonian noise due to seismic. And if you have a Newtonian noise estimate, which can be subtracted from your noisy gravitational wave data, you can get rid of it and you have a clean gravitational wave data output. This is the main principle. And now the question, of course, arises, where do you get these Newtonian noise estimate? And we have already heard about the Newtonian noise sensor, the torpedo experiment, which is one possibility, but you need maybe more of these really complex experiments at different locations around the gravitational wave detector. And another possibility, which was already mentioned before, is you have a Newtonian noise model. So here I just put you one of the Newtonian noise models, So this is the estimated acceleration, which is on a test mass due to Newtonian noise here on the left side. So this is really the gravitational force. And on the right-hand side, you see that the seismic displacement, for example, directly drives the acceleration. So it also depends on the density and volume of the ground. This is also why we, for example, need this kind of site characterization. But based on this model, it is clear if you do a seismic measurement around your gravitational wave detector, you can somehow estimate the Newtonian noise or the test mass acceleration in your experiment. What you just need is you need seismic sensors on the sides of the test masses, which are sensitive to Newtonian noise. Then you need something like a filter, which models the influence of Newtonian noise. And then you can put it in your coherent noise cancellation system. The problem is now, it was also mentioned by my pre-speakers, that you actually need a lot of sensors to get a really good estimate of your Newtonian noise. And this is one of the challenges that these kind of techniques has for example, the Einstein Telescope in the future. So I will just give you an example what Francesca and Jan analyzed. So they investigated a lot, but here just depicted on this slide, I put you the optimal sensor array for one test mass, which is here in the middle of these three-dimensional grids. And then they tried different constellations of seismometers, which are placed around the test mass. And they figured out, if they run the simulation again and again, that you need at least 20 sensors per test mass to get a decent suppression for Newtonian noise in a certain depth because of body waves. And this comes up with a number of more than 200 seismometers that you need. Really good seismometers, actually, so they need to be broadband because you are limited at low frequencies. So you need sensors which are good at below 10 Hertz. And you need a really large array which covers a kilometer range around the Einstein Telescope. So you need them in individual boreholes. So more than 200 boreholes around the Einstein Telescope, 15 kilometers, 20 kilometers away from each other. And this is, of course, really expensive. So we are also looking in other technologies for that. And this is where distributed fiber sensors actually comes into the game, because fibers are really sensitive to seismic. So they can measure the seismic strain. So they are perfect for body waves, which are compressional waves in the ground. And it's pretty easy to install them in an infrastructure. And if you do a certain technique, for example, or if you use it, for example, optical time domain reflectrometry, where you send a light pulse into a normal telecommunication fiber, for example, and you do a time of flight detection, you can actually get a spatial resolution within your fiber. So imagine that for the first fraction of the fiber, the pulse will be back reflected due to Rayleigh scattering, actually, because it's a normal telecommunication fiber. And if the first pulse arrives based on the time of flight, you can estimate where in the fiber this light actually comes from. And if there's a disturbance, which will produce a phase variation of your backscattered light, you can measure the seismic at this location. And this gives you the opportunity to just send a light pulse into the fiber and measure after 1 meter or 10 meters every time this backscattering, and then you get a really high spatial resolution just with one single fiber. And if you compare this, for example, with or put them into around a test mass for the Einstein Telescope, you can put also multiple fibers in one borehole. Is much more easier than seismometers, for example, and you can distribute them really easily. And this is what we are currently investigating in Hamburg. So this is what I already mentioned in the beginning, the so-called WAVE initiative. This is a seismic network in Hamburg, where we actually have such a distributed acoustic sensing device installed. So this is a commercial system that you can just buy and then connect to a commercial fiber, telecommunication fiber. So here you can see a map of Hamburg, and the red rectangle here shows the location of the fiber. So here in the blue rectangle, you see the DESY campus. So this is a huge research facility in Hamburg with accelerator people, gravitational wave detection experiments, and so on. So I'm also sitting here, Oliver's group also. And here you can see the blue and red lines, which is a fiber on the campus. And you can see the gray line here along one of the accelerator tunnels, the European XFL, where we also have a fiber of about 3 to 4 kilometers length back and forth. And here you can also see some triangles in the upper map of the DESY campus. These are just individual seismometers and geophones, which we have on top on this DESY campus. We set them up for a specific measurement campaign in 2021. So they are not permanently installed, but we still have the data. And I would like just to give you some impressions what we can do with this kind of seismic network. Just to give you an idea, the total fiber length was actually 12.6 kilometers. And we had a 1 meter spatial resolution within the fiber. This is pulse, laser pulse, which we sent into the fiber, which gave us more than 10,000 seismic strain sensors, actually, that we are now going to analyze. This is how such a system or such a measurement actually looks like. So here you can see on the y-axis, you can see the position of the fiber or of the strain sensor, actually. And it is plotted, and the frequency is actually plotted. So you can see that we have on the campus and also in the tunnels. So you can also see, this is actually only the tunnel section of 2000 meters. You can see individual noise sources oscillating at different frequencies. And we were actually able to monitor and localize different stations. For example, the high voltage, high frequency stations, we had some electronics noise that we could actually localize, and also some vibrations due to cooling water pumps. And of course, we were also sensitive to the traffic noise, everything which is occurring at low frequencies here. Not shown here, but we could also measure the microseismic due to ocean waves, but I think you cannot see it here on this picture. Just to give you another example, we were actually able to localize and identify an unknown noise source in the European XFL. So here you can see again the position and again the frequency, so the same plot as before. And the researchers actually claimed that they observe in their measurements an unknown noise oscillating at around 47.5 hertz. And you can already see with the dust system over the length of the fiber that the intensity goes up towards the end of the tunnel. And by this, we were actually able to identify that this noise actually comes from a helium compressor. And this already shows you what kind of potential might be in these kind of distributed fiber sensors, even though the technology is maybe not perfect, but we were able to identify and even localize noise sources. And this could help, for example, in gravitational wave detectors to get rid of seismic vibration or analyze unknown noise at low frequencies. Or as we have also learned today, it might also help in scattered light mitigation, maybe. What we also do is we compare different sensors with each other. So you have seen that we have also seismometers on the campus together with a dust system, the distributed acoustic sensing device. And here you can see during the time of an earthquake, actually in China, that we measured in Hamburg, that you can see a huge coherence between the seismometer data and dust data. So it seems like they are sensitive to similar seismic waves. But as we have analyzed the self noise of the system, so here was our setup. Here you can see actually a fiber coil in one of the tunnels. And then we just measured the same signal 3 times. We just picked 70 meters of these fibers, so about 10 windings. And then we compared the different signals with each other here and compared the different signals also to estimate the noise of the system. And you can see here at low frequencies, so below 10 hertz, where it is actually critical for the Einstein telescope, that the noise goes up. up to nanostrain per square root hertz. And this is actually quite close to the signal that we had in the tunnel. So we don't have so much sensitivity or signal to noise ratio at low frequencies. So even though the dust system already shows us a lot of noise sources and can also help to localize noise sources, at low frequencies, the noise goes up and we might be actually limited by the system. So this is why we are also looking into new kind of techniques, especially for the Einstein telescope, to improve the low frequency performance. And this slide is again really easy for me because this technique called digitally enhanced heterodyne interferometry was already mentioned today. So the ANU also uses this exactly same technique for novel suspension platform interferometry. So the idea is that we use an engineered fiber, so not only a normal telecommunication fiber where we measure the backscatter. You can imagine that the signal is really low in power because we only measure the Rayleigh backscattering, but we can improve the signal by just placing some mirrors into the fiber, for example, fiber back gratings or other technologies. And then we need a dedicated readout system, which can read out these individual back reflections in a fiber. And we have already learned that digitally enhanced interferometry allows for multiplexing. So you modulate a pseudo-random noise code onto your laser. And by this, and again, a time of flight measurement, you are able to extract the individual signals from each other on a single optical axis. And this is actually what my group tries to implement on the Hamburg campus. So I will just give you a very old result of an experiment that I did in Hanover. So we used a really, really fast modulation, which in principle gives you a spatial resolution of only 12 centimeters. And we also have seen some experimental results before. And it shows that you can actually reach here in the null stream measurement. So this is again the sensing noise of the digital interferometer, while in blue you have the raw mirror motion in the setup, that you can achieve something like 20 picometer per hertz at 1 hertz. And if you then calculate it down to 1 meter again, 1 meter spatial resolution, you might end up with 20 picostrain, which gives you 2 orders of magnitude improvement over the current systems, the current dust systems that we have. And what should also be mentioned here, that this was a free beam setup. Of course, later, if we do this in fiber, we will have additional fiber noise and laser frequency noise and so on. But here, this was a measurement done in air, just by comparing 2 reflections of 2 mirrors. So a lot of air density fluctuations can also be rejected by common mode rejection, actually. So if you have a reference mirror, you can actually get rid of common mode noise sources. So this is another advantage of digital interferometry to improve the sensitivity also at low frequencies. So the plan would be for the Einstein telescope that we build up such a prototype experiment where we have this digital interferometer with hundreds of channels, which can provide a fiber link to individual fiber sensors. Each is placed into a borehole, or maybe several ones are placed into a borehole. Or you also do fiber back ratings within one fiber. And just by inserting a delay, you can read out multiple fibers in multiple boreholes just with a single device. And this is, of course, a big advantage. And what we are also working on in parallel, so this is also ongoing, so I cannot show any results yet, but you might know that for these Newtonian noise cancellation systems, we also need to know where to place the sensors actually to get the best suppression. So what we are currently doing, we are doing the Newtonian noise cancellation simulations together with Francesca and Jan to estimate or to get an idea how many strain sensors we actually need and whether they are sufficient to get rid of Newtonian noise in the Einstein telescope. And with this, I think I'm already done. So conclude my talk. The dust system distributed acoustic sensing can help, or maybe also the current gravitational wave detectors, to improve their sensitivity. So for example, we have shown that we can identify and localize noise sources. We can also monitor vibration, seismic, and then maybe get rid of scattered light in the tunnels or in the vacuum chambers. And we can also investigate the currently unknown low frequency noise in the current detectors. However, for the next generation of gravitational wave detectors, like the Einstein Telescope, which requires Newtonian noise cancellation systems, we need improved strain sensors, because the current systems might have not, or it seems like they don't have such a good broadband sensitivity below 10 Hertz. This is why we want to use digitally enhanced interferometry and also investigate new fiber sensors and start new simulations on optimal strain sensor arrays for the Einstein Telescope. And if you have further questions, just ask me now, or you can also write us an email. So yeah, thank you for your attention.
Thank you very much. Are there any questions? Oh, there's a question. Okay, Sheon, please.
Oh, hi. Yeah. Yeah, thank you for the talk. Just a very quick question. So yeah, I'm excited to see the patterned fibers being deployed. So yeah, my original question was about signal to noise. Well, if you put Bragg gratings in your fibers, then of course the signal goes up by quite a lot. My question is, do you have like an idea or a plan to like how like the numbers or the densities of fiber Bragg gratings you would put in a fiber, or is it just like a nominal value at the moment?
Yeah, so yeah, to be honest, we need to repeat all the optimal strain sensor simulations that has been done by Francesca and Jan for seismometers. Just from their simulation, I can conclude that you need in an environment of multiple kilometers. I mean, it depends on the seismic wavelengths, of course. So you need to get a sampling of your seismic wavelengths in the spatial domain. So this gives you the distance between two seismometers or strain sensors. So I think we should come up with a similar number than they came up with the seismometers, but I don't know if a compressional or a strain sensor measures enough of these seismic waves and produce a Newtonian noise. So I think 10 meters is more than enough that we need for such strain sensors regarding the spatial resolution. I think even 100 meters might fit to some certain seismic wavelengths. Yeah.
Great. Thank you.
Any other questions? Seems not. Then yeah, thanks Kata, and also thanks again to all the speakers of this session. So we are finishing just in time, which is great. So yeah, thank you all, and have a good day.
Thank you.
Thank you. Bye.